So here we have a wall form design example that we're going to run through. This one is similar in style to the one that you did in the worksheet in class, so we'll go through it fairly quickly. What you're going to need is this problem statement here. There's a small diagram of the situation that we're looking at right below it. Also going to make sure that you have this document available with the equations and all the tables with the data that we're going to be pulling from for this problem, and then we should be ready to go. So take a quick look at this, pause it if you need to write down all the givens, and then go ahead and push play and we'll go ahead and solve it. So we're looking at wall, 12 foot high. Here's the rate, here's temperature, the weight, the type of concrete, and then here's some of our initial design assumptions that we're going to use. And then we're going to see if that design is okay, if it's over-designed, if it's under-designed, and what we need to do to adjust it. So there we go. Alright, so first step in these problems is we're going to find the design load. So this is pretty critical because all of the rest of your equations are going to use this number in order to check and find your spacing. So looking at this table here, you need to look at the parameters of the problem and basically pick between these three possibilities. In this case, we've got a rate of placement between 7 and 15, but our height is less than 14. So we're good here. This is going to be our equation that we're going to use. So let's go ahead and do it. So step one is our design load. And that's going to be P is CW CC 150 plus 43 400 over T plus 2800 R over T. Okay, so let's get some of these variables here. We said that the temperature here is 95, so that's T. We've got R was 12 feet per hour. The weight, W, is 130 pounds per cubic foot. And then now let's find this CW. So CW, going back here to our chart, here's our CW chart. We're under 140, so we have to use this equation right here. So CW is equal to 0.5 times 1 plus the weight over 145, and then that comes out to 0.5 times 1 plus 130 over 145 equals 0.95. Okay, then C sub C, so that was the weight factor. Here's the chemistry factor here. It's 1.0. We get that from the next chart down, which is C sub C. Type 1, 2, or 3 without retarders is 1.0. So 1.0. Alright, so we'll go ahead and find our P now. Is 0.95 times 1 times 150 plus 43 400 over 95 plus 200 or 2800 times 12 over 95. And you do all that out and you get 912.5 pounds per square foot. Alright, so let's keep that one in mind, and then when we're looking at our next steps here, we're going to find 2 is going to be our pliform design. So we're going to check our pliform design, make sure it's adequate, and also we're going to be finding stud spacing at the same time. Okay. For this problem, we're going to assume 3 or more spans. And that'll come into account here in a minute. So basically what we need to do is we're going to look at just a 1 foot section of our sheathing here. So if we're going to take this pressure value and turn it into more of a load over the length, we're just going to take this 912.5 pounds per square foot, we're going to multiply it by 1 foot strip of this pliform, and we get 912.5 pounds per foot. And that doesn't seem like it's a big deal, but later on when we have kind of different spacings and whatnot, this number could change. But just conceptually, so we can get from a pressure to kind of a weight distribution along 1 foot. Alright, so what we're going to do is we're going to look at the spacings that we get looking at different mechanisms of failure. So the first one we're going to look at is the bending of the pliform. So here we're looking at this table. Let me get the right one. Here we go. Okay, so 3 or more spans. We're looking at plywood for bending. So here's our equation right here, 10.95. And just for simplicity, so we don't go back and forth, we're going to use this equation for bending, we're going to use this equation for shear, and we're going to use this equation for deflection. Okay, so bending, we're going to get our spacing is 10.95 times FB KS over W to the 1/2 or square root. Okay. So what is this FBKS? Well, that also comes from a table, and I'll show you that table here. FBKS is here in our section properties of plywood table. So FBKS for face grain parallel to support or face grain across supports. In this case it's face grain across the supports. We're using 7/8 pliform class 1. So you come over, FBKS is 1.127 times 10 to the 3. Don't forget, to add these 10 to the 6, 10 to the 3, 10 to the 3. That'll come in handy later. So just for simplicity, this is the table that we're going to get EI, FSLB over Q, all are going to come from this table, so we don't have to refer back every time. Okay, so in this case, FBKS is 1.127 times 10 to the 3. So we plug this in, we get 10.95, 1.127 times 10 to the 3 over W, which we found here is 912.5. Take the square root of that, and we get L here for bending of 12.17. Okay, so next we're going to check shear. Check the shear failure mode, its maximum spacing. So from that other chart that we talked about, we get 20 FSLB over Q divided by W plus 2D. This FSLB over Q from that chart was 0.613, or sorry, 616 times 10 to the 3. And so we plug this in, L equals 20, 0.613 1/6 times 10 to the 3 divided by 912.5 plus 2. We're using 7/8 thickness plywood. So we get an L, in this case, of 15.3 inches. Okay, last we're going to check the deflection failure mode. Remember the problem said for deflection of L over 360, so we use the table corresponding to that value to get the equation of L equals 1.69 EI over W to the 1/3. EI in the table was 0.444 times 10 to the 6. So we get 1.69, 0.444 times 10 to the 6 divided by 912.5. All that to the 1/3. We get a spacing for deflection of 13.3. So looking at this number, and this number, we choose the smallest. So it looks like bending governs in this case at 12.17 inches. So we will use a stud spacing of 12 inches. Okay, so that's that. And then next step here is to check the stud design and the wale spacing. So number 3, put check studs / wale spacing. And this is really almost exactly the same as the previous steps, only we'll need to look at different charts to get some of these equations. So we need to make sure again that we're using the right loading. So we're going to use W was P, the original P that we had of 912.5 times the spacing of the studs. Okay, so we get W equals 912.5 times, we used a 12-inch. And there's 12 inches in a foot, so that ends up giving us 912.5 again. But this, you just need to make sure that you're doing this every time, and you'll see why. Sorry, that's a foot. As it changes in the future. It just happened to be 1 foot again. Okay, so again, we'll check bending. And to get bending for our studs, we go back to this chart, and we're no longer looking at the plywood equations, we're looking at the wood equations. So we're going to go ahead and use these equations here. We're going to use this wood equation here, and then we're going to use the deflection equation here, which there's no distinction between wood and plywood. And then further, when we're looking at the properties of these for a 2x4, here's our actual size, the nominal size, area, section modulus, moment of inertia is all in this chart. So that's what I'll be drawing from for these. And then further, when we check it against our actual allowable stresses, we're looking at the Douglas fir larch and all of these values for E, bending force, shear, compression, etc. Okay, so bending, we're going to use the equation here. L equals 10.95 FB S over W to the 1/2. And FB from that chart with the Douglas fir larch is 1450. S is 3.063 inches cubed. And we know our W from up here. So we get our spacing of 10.95, 1450 times 3.063 divided by 912.5, all that square root. We get a spacing of 24.2 inches. Okay, so again, we're going to check shear. Going back to the table, we're going to get our shear equation to be 13.3 times FV A over W plus 2D. So FV from the chart for Douglas fir larch is 185. The area is going to be 5.25 for a 2x4 inches squared. And D, yeah, we got that. So we'll plug it in, 13.3, 185 times 5.25 divided by 912.5 plus 2 times D is 3.5 for 2x4. And we get a spacing here of 21.16. Okay, and last deflection. We're going to use the equation from that chart that showed L equals 1.69 EI over W to the 1/3. E is 1.7 times 10 to the 6. I is 5.359 for 2x4. And we get 1.69, 1.7 times 10 to the 6 times 5.359 divided by 912.5, all that to the 1/3. We get a spacing of 36.4. So looking at this, we've got 24, 21, and 36, so our shear governs in this case. So we're going to use Wales at, we'll say, 18 inches. Okay. All right, so next step here, we're going to kind of do the same thing. We're going to check the whale design / find the tie spacing. Okay, so in this case, always starting with our load per unit length. In this case, we have our overall loading, or our pressure, 912.5 pounds per square foot. And then we have to look at the spacing of our whales, which is 18 inches divided by 12 inches in 1 foot. Make sure you make that conversion. And we get 1369 pounds per foot. So this is why it's very important to do this step and not always just use this value, because if your spacing is not 1 foot, then you need to make sure that you're looking at the actual amount of force per unit length on the item that you're designing. So again, going through bending, and just a reminder, we're going in that chart that we showed. So again, these equations are all going to be exactly the same as these up here. We're just going to be using a couple of different items for these ties. So the ties, if we go back to here, you can see the ties are here, and there's 2 2x4s sticking through these ties here. Okay, so that's important to remember, and make sure that you get that from your problem statement, or if you're designing it, it's pretty typical design so that you don't have to actually drill through your tie spacers. So bending, I'll run through these real quick and we'll just get, actually, I'll just put out the spacing. So bending, the only trick here, make sure that when you find S, I'll put that here, S equals 2 times 3.063. Up here we just used 1, down here we've got 2, so that's important. Okay, but that spacing that we end up with is 27.9. Okay, B shear, we're going to use for shear an area of 2 times 5.25. So we get a spacing for shear of 25.9. And then last is deflection. And for deflection, E is the same I. The moment of inertia is going to change to 2 times 5.359. So we get a spacing and deflection of 40.05 inches. So again here, shear governs 25.9. We'll use ties at 24 inches. Okay, so next thing to check is to make sure at this spacing that the ties can handle it because they have a capacity. So we're going to check the tie capacity. So how much load is the tie actually holding? I'll call that P sub T is going to be the wale spacing. Times the tie spacing times your pressure, P. So the wale spacing was 18 inches. The tie spacing we just found to be 24 inches. So let's put that in. So 12 inches, I'm sorry, 18. We used 18. And we'll just put that over 12 times 24. That's what we just designed. Times our pressure of 912.5. And this is the actual force that's on this. So you can see that we have an area here. This is its tributary area, and this is the pressure. So doing that, we get 2737.5 pounds, which, going back to the problem statement, they were 3,500 pound capacity, so we're okay there. All right, so moving on then, let's check bearing. So we're going to do bearing. Just kind of looking at compression failures or crushing. So first one we're going to look at are these studs on the whalers. Okay, so P in this case is going to be the load per foot times the wale spacing. So this is how much force is actually going to be on these studs at the contact area. So that's 912.5 pounds per foot that we found from previous parts of the problem times the wale space is 18. So we get 1368.8 pounds. Now we need to look at, so if we're looking at compression, we're going to take that P, divide it by the cross-sectional area that's holding it, and we get 1368. Divided by the area, which is 4.5 for a 2x4 set on the side, equals 304.2 psi, so that's pounds per square inch. And looking at our FC prime, or FC perpendicular max from the chart here. See perpendicular max, Douglas fir larch, 385. We're okay. So 304 is less than 385. So we're okay there. So we're getting failing bearing on the studs on the whales. Now let's look at the ties. Kind of the tie wedges on the whales. So again, let's look at the tie load. So the load on the tie. P is something we already found right here when we were looking at tie capacity. Is this number right here. So 2737.5. The area is going to be 4.5. This is 1.5 times 1.5 times 2, because we're looking at kind of the ties here and the wedges that we're using here. So here's the area that we're going to be using. So we get FC equals P over A equals 2737.5 divided by 4.5 equals 608.3. And that's much greater than 385. So that's not okay. So what can we do about it? Well, there's two things we can do, and this is where kind of the iteration process comes in if you were to be trying to design this. One thing we can do, one option, is use smaller spacing. So if we use smaller spacing, that affects the load on the ties right here. So if we use the tie space and decrease this from 24, then we could get it good. So let's, I already did it kind of, but let's use 12-inch spacing. If we use 12-inch spacing, you can go ahead and do the math. We come out with 304, which is less than 385, which works. The other thing we can do is use bigger members as our tie wedges or tie spacers there. And if we end up using an actual dimension of 2-inch by 2-inch, just to do the math, not a very common size, but we end up with 342.2, which is less than 385. We would check out. So we would need to make some modifications to our design in order to make these not crush. All right. So that's this problem.